Hi everybody, welcome back. In this video, we're going to go over section 2.7, which is all about density in your textbook. And then at the very end of the video, we'll take a short detour to talk about section 3.4, which is about energy. But we're not going to go super in depth in there. We're just going to go talk about it a little bit. So density is something that you might be kind of familiar with. So if you look at this phenomenon over here, you can see that in water, objects that are more dense than water are going to sink to the bottom, and objects that are less dense are going to float to the top. Okay, and density is actually just can be expressed as a relationship between the mass of a substance and the volume of a substance. Okay, so usually mass is measured in grams, and then volume can be measured in different things depending on the state of the matter that you have. But usually maybe mils, especially if you're dealing with liquid volume, the volume of a liquid. Okay, and then density, the symbol for density you might see as the Greek letter rho. It kind of looks like a P, but it's spelled like that. It's almost like a, kind of like a cursive P. All right, so by the end of this video, I want you to be able to calculate the density of a substance and then use the density to calculate the mass or volume of a substance. So notice that this is a mathematical equation, right? This here. So you can actually, if you know two of any of those values, you can calculate for the other, you can solve for the other one. All right, here's just a table of some densities of common substances. So helium, you might recognize, that's the gas that they put in balloons. Helium is very light, so its density is pretty low, and that allows us to have balloons that float in the air, right? Because air, dry air, has a higher density than helium. This is kind of interesting to look at, and you'll also notice like water at 4 degrees Celsius has a density of 1 gram per mil, 1 gram per mil. So kind of interesting. And then you'll notice that the temperature actually affects what the density is. So they're always like reporting like at 25 C, at 25 C, at 0 C. And we'll talk about why that is in the future. So for calculating density, again, here's your mathematical equation. You'll also see it sometimes written as D equals M over V with a capital D, lowercase m and V. And that just stands for mass, volume, that's a lowercase v, sorry. And density. Okay, so you can write it like that as well. So for density of solids, we actually represent that number in, actually let's go green for solids. I don't know why, that just makes sense in my brain. So for solids, we actually represent density as grams over cm cubed, centimeters cubed. And the reason for that is, like, remember, when you have a solid like this, you can measure the sides, the length of the sides, and report that like this, cm cubed. Because remember, you have an imaginary 1 for each of these exponents, and then when you're multiplying those, you're actually adding the exponents. Okay, so that's how we report the density of solids. Okay, because this is how we can more easily find the volume of a solid. All right, and then for liquids, let's go blue for liquids. We report it like this: grams per milliliter, or mil, grams per mil you'll often hear. And then for gas, we often report it like, I guess we'll go yellow. We often report it with grams per liter. But every number that's on the bottom is always a measure of volume, and every number on the top is always a measure of mass, and that checks out with our equation here. Okay, that's how we report density. Okay, and then just a note, let me move this here up a little bit. Just a note that looking here, 1 milliliter is actually equal to 1 centimeter cubed. Okay, so these two are actually the same value. If you have 2 centimeters cubed, you have 2 mils. If you have 3 centimeters cubed, you have 3 mils. They have a 1-to-1 ratio. Okay. All right, so density of solids. I thought I had another slide in here. Okay, that's interesting. All right, I thought I had another slide. Sorry. So for density of solids, the density of a solid can be determined by dividing the mass of an object by its volume, determined from volume displacement. We're actually going to do this in lab. So for things that are shaped, like this, we can do that method where I'm just, sorry, I'm really bad at drawing 3D. We can do that method where we just measure the sides of things, right? We can take a ruler and we can measure this length and this length, but there are some things that are weirdly shaped and they're hard to measure. What if you have a rock that you're trying to measure that looks like that? Those kinds of things, we're not going to like take a ruler and measure each of these curves, and it would be inaccurate to do so. So for those cases, we like to measure by displacement. Okay, and you can measure any volume of a solid by or density of a solid by displacement, because like even if you wanted to just measure that cube, you could by displacement, right? You could do that as well. So for like very small objects, that would be more practical. Okay, so the way that we do that is we put a liquid in. This is a graduated cylinder. We put a liquid in some kind of measuring device, and we measure how much liquid we have in there. Okay, so we measure how much liquid we have in there, and then we submerge the object that we're trying to determine the volume of. So we submerge this thing in the water over here, and we determine how much did the water move, how much was the water displaced by that object, and that tells us, that difference here tells us how what the volume of that object is. Okay, and we'll do this in lab. So, for instance, the density of a solid zinc object is calculated by dividing its mass by its displaced volume. So determine the displaced volume, submerge the solid in water so that it displaces water. Oh, sorry, I sneezed. So that it displaces water, and that displaced water is equal to its volume, okay? So, sorry, I was checking. Okay, yeah, this is the same example. So that's where I was wondering where they were getting these numbers from, and that's because we have them up here. So what they've done here is they've taken the volume that we started with, 35.5 mils, and subtracted that from the volume that it was displaced to. And since we're just calculating the distance between these two measurements, we can just put the larger number in front so that we don't end up with a negative number. And you'll get used to that more in chemistry when we do work with those numbers more. So, and then they got 9.5 mils out of that calculation when they subtracted those two. And since it's a solid, they're actually going to report that in 9.5 centimeters cubed. And remember, that's because 1 mil equals 1 centimeter cubed. They are exactly equivalent. So we don't even have to change this number. We just change how we're reporting those units because we have a solid. Okay? All right, and then once we have that volume, remember, what we just found out here was the volume. This is the volume of our object, in this case, zinc. So we just found the volume, and we can figure out the mass by weighing it. So we take our object, we place a little weigh boat on, that's what this is. We place our little weigh boat on there, press the tare button, which is also like called the zeroing. You're zeroing your scale, you're pressing tare. And that makes it so that once you put the weigh boat on there and then you you tear that, that, what's it called? The scale. Gosh, I'm sorry, you guys. So you tear the scale. You're probably screaming at the screen like, scale, scale. And then you put your object in there. And then it's just going to measure the mass of this object instead of this wayboat as well. And we'll talk about how to do that in lab, and I'll explain it again and actually show you. But so they measured the mass of this object and they got 68.60 grams. So that's where this number is coming from. Okay, and that's the mass, right? So we're measuring the mass of it, and then we're also measuring the volume, okay, which we got from here. And then we we carry out that calculation, and we get our density, right? Because density equals the mass over the volume. Density equals 68.60 over 9.5. And then we report that in grams per centimeter cubed because we have a solid piece of zinc. Okay, if we were measuring some kind of liquid, we would report that in mils. That's just the convention. Okay, all right, I hope that makes sense. Okay, so we can also problem solve using density. So if the volume and the density of a sample are known, the mass in grams of the sample can be calculated by using density as a conversion factor. Okay, you could also just think of it as D equals M over V. If we know this, and we know, what else did it say we knew? The volume and the density, we can solve for our unknown, and this would just be our X. So say our density was 4 and our volume was 2, we could plug those numbers in and solve for our unknown. Okay, but you could also think of it as a conversion factor. So let's look at this here. So an unknown liquid, so we don't know what liquid it is, but we know it has a density, an unknown liquid has a density of 1.32 grams per mil. 1.32 grams per mil. So when you're looking at this number, let's just pause for a second. We can write this as a fraction, as a conversion factor. So we can say 1.32 grams per mil. Okay, so this here, that little division sign, that's what you could call you could say that's your per. Per. So 1.32 grams per every 1 mil. Okay. So that's your density. And you can write that as a conversion factor. So remember, with conversion factors, you can write 1 mil on the top and 1.32 grams on the bottom. 1.32 is in the numerator though, because it kind of goes with this, grams per every 1 mil. Okay, so if you had a number like 4.00 grams per mil, you would again write that 4.00 grams per 1 mil, or 1 mil per every 4.00 grams. Okay, you could do either of those. Those are your conversion factors. All right, let's keep going. So, sorry, I got an email there. What is the volume in mils of a 14.7 gram sample of that liquid? All right, so again, what are we given? What are we given? Let's highlight it. We're given that we have a 14.7 gram sample of our liquid. So let's go ahead and write our our dimensional analysis problem. So we start with 14.7 grams. And then let's go ahead and set up our train tracks. Okay, so 14.7 grams. How are we going to get to, what's our goal? What's our goal? Yeah, our goal is to get to volume, the volume of that liquid. So how are we going to get from grams to mils? Well, we're going to use the density. We're going to use the density because that's connecting our grams and our mils, right? And we know the density of our liquid. We're told it. Okay, so we've got 14.7 grams in the top. What goes in the bottom? Grams or mils? What do we want to cancel out? We want to cancel out those grams to be left with mils. So we got to put grams in the bottom. So how many grams? Well, we're going to use this conversion factor. So 1.32 grams. And what goes in the top? 1 mil, right? Kind of cool, huh? I think so. Okay, so now we can cancel out our grams. Cancel that out, because we've got them on the top and the bottom. And we're left with mils. Is that what we were trying to get to? Yeah, we wanted mils in the end, right? We wanted to measure the volume, okay? So we can say 14.7 times 1. Remember multiplying everything on the top and dividing by everything on the bottom. So 14.7 mils over 1.32. Let's do that calculation. 14.7 divided by 1.32 is 11.13636 ... mils. Okay, are we done? No, we're not done yet. We gotta make sure we got our sig figs, right? So let's go ahead and make some erasing. Let's erase some of this stuff. Okay, so how many sig figs do we have here in our measured value? We measured that, right? We said we have this many grams of sample of our liquid. So someone measured that in lab. So that is 3 sig figs. Okay. The density is actually an exact value. So you don't need to worry about sig figs for this part. Okay. But we do want to worry about sig figs for this. So 3 sig figs. So we got 1, 2, 3 in the top, or sorry, 1, 2, 3. Wait, so we want to go to this digit. So we're going to look next door. Is that digit higher than 5 or lower than 5? It's lower, so we're just going to leave it at 11.1. So 11.1 mils. Okay. All right, let's go ahead and end the video there. They do show you the solution, but I want to switch to something else next. Okay, so yeah, so we're good. All right, see you in the next video.